this session. And let me ask you this. Any problems that you have for tonight? Are you able to verbalize them, or are they graphical in nature such that I would need to look at it?
No, I can verbalize them.
Okay, go ahead. That's actually the best way to do it. That's really better than if you send it to me. It's just that some problems can't be verbalized. You know, if they give you a graph and they say, come up with the equation of that line, you're not going to be able to verbalize that to me. But if it's just a regular algebra problem, you will be able to.
Okay.
What's the problem? I'll write it and then we'll solve it.
Okay, well, we're solving quadratic equations right now.
Okay.
And the problem she gave me was 24 plus 10x minus x squared equals p minus, and then in parentheses, x minus 5.
Did you say T?
P.
P.
Yes.
And then in parentheses, x minus 5, like that?
Yeah, p minus x minus 5. And then squared.
The whole thing, like that?
Just the x minus 5.
Okay. Well, right off the get-go, there's a problem here. The problem is we have two variables. We have an x and we have a p. That means we're not going to be able to solve for x. If you have one equation and one variable, you'll always be able to solve for that variable. But if you have one equation and two variables, it's impossible. You cannot solve for either variable. Now, what are they asking you to do with this?
Well, they said to find p.
Okay, so they want you to solve for p. We can do that. We can do that. Okay. The first thing is let's expand this x minus 5 squared.
Okay.
So, and let's keep our parentheses so we don't get confused. What is x minus 5 quantity squared?
So, it'd just be x minus 5 times x minus 5, right?
Yeah, do that multiplication, FOIL those two, what do you get?
So x squared minus 5x minus 5x minus 25?
Plus 25.
Oh, right.
That last term is minus 5 times minus 5.
Yeah.
Okay. Now, let's remove those parentheses from the right side. What do you get? In other words, whenever you're solving equations, a really good rule of thumb to use is get rid of your denominators, get rid of your parentheses, then proceed. Well, we don't have any denominators, but we got parentheses here that are kind of mucking things up. So if I remove these parentheses, what do I have?
You just have negative x squared minus 10x
plus 10x. In other words, this minus sign has to be applied to every term in the parentheses. That's why the parentheses are so important.
So would it be a minus 25?
Yes.
Okay.
Okay. And now, if I go ahead and put the left side on this equation, which nothing's changed over there. Now this is what I'm looking at. And I want to solve for p. So I want to end up with p all by itself. Okay? So I got to get rid of everything else. Everything that I put that little rectangle in. How do I get rid of the minus x squared?
Add it to the other side?
Yeah, it turns out there's a minus x squared on the other side, so those just cancel.
Okay.
Now, and let me take away that box because it makes it look like I'm multiplying. So, and I'm not. Very important to distinguish between multiplying and adding or subtracting. How about the 10x?
You can subtract that from both sides.
Yeah, that gets rid of that. And I'm left with p minus 25 equals 24. What's p equal to?
Okay, so I have to add. So p equals 49.
Yeah. So immediately it contradicts me.
Yeah.
In other words, I started off this problem saying there were two variables, one equation, we're not going to be able to solve for the variable. Well, it turns out that because the x's both canceled, the x's went away and I was left with only one equation and one variable, which was p. So in this particular case, I actually was able to solve for p. And it might not be obvious, but x can be any number. Does not matter. X can be any number on the number line.
Okay.
And as long as p is 49, this will be a proper equation. Okay? But this is quite unusual. Usually you cannot solve for a variable if you have two variables and only one equation. Like I said, the only reason we were able to is because the x squareds went away and the x's went away. And we were left with nothing but a p and two numbers. What else you got?
All right, well, there's another one, and it says solve the system using substitution and elimination, and it gives me three equations.
Okay.
Or, well, three different variables. But the first one is 2x minus y plus 2z equals negative 7. And then the one underneath that is negative x plus 2y minus 4z equals 5.
And I need a third one because right now I have three variables and two equations. You cannot solve that system. As long as you have the same number of variables as equations, you can always solve it. What's the third one?
X plus 4y minus 6z equals negative 1.
All right. There's a method that you want to use here. These are hard problems. They're not hard, they're lengthy. You're never going to find more than one of these on a test because each one is like a 10-minute problem. We'll be lucky if we solve this by the time our session or by the time your brother's ready to come in.
Okay.
Here's what I always recommend doing, and that is numbering these equations. And the reason is you're going to end up with a whole page full of equations here. And you want to keep them straight. Okay? So, step one, my plan is to create an equation number 4, missing a variable, and an equation number 5, missing the same variable. So I'm always allowed to add or subtract equations. Can I eliminate a variable? And incidentally, whenever you get these problems with 3 variables and 3 equations, you're always going to want to use elimination, never substitution. It's not that you couldn't use substitution, it would just be a lot harder. Elimination is really easy here. And so I have never seen a problem with 3 variables and 3 equations that you solve by substitution. It's always elimination. So look at these 3 equations and tell me, can I add or subtract any two of them and eliminate a variable?
Just with how they are?
Yeah, without doing anything to any of them. Is there a simple first step that lets me generate equation 4?
No. Oh, wait.
How about if I add 2 to 3?
Yeah, you can eliminate
What do you
the
get? Yeah, okay, so what do you get when you add 2 and 3?
But x's cancel out, so it would be 6y minus 10z equals 4.
Yeah, that's my equation 4. And you'll notice
Okay.
that x has disappeared. So now the goal is to add any of the other two. In other words, I could add 1 to 3 or 1 to 2 and try to eliminate the same variable to come up with equation 5.
Okay.
Well, I can't immediately do that, but if I manipulate equation 2 a little bit, then I could add it to equation 1 and get x to disappear. How do I have to manipulate 2?
To get the x. So we're getting the x to disappear?
Yeah, we're trying to create another equation where x will be eliminated.
Okay, and so we're manipulating equation 2 to fit equation 1?
Yeah, what can I do to equation 2?
You have to
multiply it by 2, right?
Right, yeah.
Okay, so here's my new equation 2. I have to multiply every single term by 2.
Okay.
Okay, just to keep things straight, I'm going to draw a line through that equation 2. My new equation 2 is down here. It's actually exactly the same as my original equation, only it's multiplied by 2. And you can do that as long as I multiply the left side by 2 and the right side by 2. They're the same equations. Okay? Now, what can I do to eliminate x?
Well, I have to add it to equation 1.
Right. In other words, my very first step is I added 2 and 3 together. So I can do any other combination I want as long as it's not 2 and 3.
Yeah.
So I can definitely add equation 1 to my new equation 2, producing equation 5. What is equation 5 going to look like?
It is going to be 3y minus 6z equals 3.
Now what you have is a simple problem. You've done lots of these, where you have 2 equations and 2 unknowns.
Yes.
Okay, so let's solve this system of 2 equations and 2 unknowns. I'll scroll down a little bit to give us some room. Well, again, I want to use elimination to try to get rid of y or z. What's the easiest way to get rid of one of those variables?
Probably to multiply 5 times -3.
If I multiply by -3, I'm going to have minus 9y.
Oh, I mean,
You meant -2. Okay, so I'm going to multiply that by -2. I'm going to multiply this by -2. I'm going to multiply this by -2. That's my new equation 5. Now, I can add equations 4 and 5 to come up with what?
To come up with z.
Well, add those two together. What do you get?
So 2z equals negative 2, and
So,
then divide that by 2, and z equals negative 1.
yeah. So now I've solved for one variable, okay?
Okay.
And that's a key. Now all I have to do is work my way back through all of my equations, and I can certainly solve for y using that equation, but let's not use that equation. Let's use the original equation 5. It's smaller, right? All the numbers are smaller. So let's go back in and erase the line that I drew through it and use this equation here to solve for y. How would you solve for y?
You'd plug in, so you just like leave 3y and then minus 6 times negative 1 equals 3.
So now we have 3y plus 6 equals 3.
Oh, right.
3y equals minus 3. Y equals negative 1 also. Okay. So now we've solved for two variables. Now we have to go back to usually one of the original three will be a good one to use. Again here, I could use any of these equations because I've already solved for y and z. So I can come up with x. Which of those equations should I use? Which one's going to be the simplest to solve for x?
Probably equation 3.
I agree. For two reasons. First of all, the x has a positive coefficient, plus 1, not minus 1. And all my numbers are relatively small. I got a 4, a minus 6, and a minus 1. Okay, so I'm going to use equation 3, and I get x plus 4 times y was minus 1, minus 6, z was minus 1, and all of that's equal to minus 1. So now what does that give me? X minus 4 plus 6 equals minus 1. That's x plus 2 equals minus 1. X equals minus 3. There's your three solutions. Y is equal to minus 1, z is equal to minus 1, and x is equal to minus 3.
And then you could just plug that in to make sure.
Right. If you're checking to make sure that those are the correct answers, then you can use any equation you're looking at on the page. Let's try equation 1. Since we didn't use that to solve for anything, well, does that work? 2 times minus 3, which is what we got for x, minus a minus 1. Very important, do not drop negative signs.
Okay.
In other words, you should always write it out exactly like this to begin with. Don't try to do two steps in your head at once, because that's how you end up dropping negative signs. Real easy to drop negative signs in math. Now we got minus 6 plus 1 minus 2. Is that minus 7?
Yes.
That's all we need to do. I mean, if your life depended on it, I might plug it into equation 2 and equation 3 to make sure that all three work. But if you're just taking a math test and you had time to check your answers, you've just done it.
Okay.
And that's sufficient. Just use one equation to make sure that that equation is still valid when you plug in your three answers.
All right.
Okay. Let's see. Your brother's supposed to come on at 6, is that right?
Yes.
Is he going to use the same computer?
Yes.
So I don't really need to log out of GoToMeeting and log back in. So this is one of the few times that I'm not going to generate a new meeting ID number.
Okay.
I could, I'm recording this, so you'll be able to see this session as a recording, but if I use the same meeting ID number for you and your brother, the whole recording is going to be, the first half hour will be you, the second half hour will be him, which is fine as long as that's okay with you.
Yeah.
If, I can imagine there's a lot of brothers sisters out there that they'd want their own recording. In which case, I would log out of GoToMeeting, I would log back in, and I would send your brother a new meeting ID number. But as long as you guys don't care, then you can just kind of bring your brother on and we'll go from there. Let's see, he's taken Algebra 1, right?
Yeah.
Which means he should be able to verbalize most of his problems also.
Yeah.
Why don't you put him on, put Nick on, and I'll do a half hour with him under these exact circumstances.
Okay, well, do you want me to give him...
You don't need to. As long as you're going to be on the same computer, you don't need to log out and log back in.
Okay.
Okay.
Well, he's coming on now, but I have to leave, so should he call you on his phone?
Oh, yeah. Why don't you have him do that?
Okay.
I forgot for a moment that we were using the speaker on my phone. Okay, so I will hang up the phone with you and have him call me at my number. You have my number there, right?
Yeah.
Okay, have him call that, and he and I will use the speaker also.
Okay.
Okay, Anna, I will talk to you next time.
All right, well, thank you.
You're welcome. Bye-bye.
Bye.
This must be Nick. Excuse me, I didn't have my speaker on for a moment. Nick?
Yeah?
Yeah, hi. This is David. How are you?
I'm good. How are you?
Good. So you're on the same computer that your sister was just on?
Yeah, I'm on the same one.
And you can see my desktop? What number did I just write?
8.
Okay, cool. And that's the way this works, is whatever I write is going to show up on my screen, and if I want to write an equation like that, then we can solve it, okay? Now, you're taking algebra, so in all likelihood, you can probably verbalize problems to me, as opposed to needing to send me a picture of the problems. In other words, if your problem was like this and they said, give me the equation of that line, then I'm going to need to see a picture of it.
Yeah.
But if they say to you, if they give you an equation and they said, graph that equation, you can verbalize that to me. And we can both graph it or figure out how to graph it. Okay? So that's what kind of is important as to whether you're able to verbalize problems or not. Now, what I've found is that most algebra students, their problems can all be verbalized usually, whereas geometry students a little different. You know, in geometry, they're going to give you a graph like that, or a triangle, and they're going to label different angles, and then they're going to say, what's that third angle? Well, that's difficult to verbalize. So if you had a problem like that, you'd want to send me a picture of it. Okay? But let's try to have you verbalize. There's actually quite a bit that is learned by the student when you have to verbalize problems. The reason is that that's something you rarely get a chance to do in class. I mean, how often does the teacher call upon you to stand up and verbalize a problem? Probably never. Yeah. Okay. Well, you can learn a lot by verbalizing problems. For one thing, you can learn proper ways to state functions, and it allows you to organize your mind a little better. So what kind of problems are you guys working on right now?
We've moved on from graphing.
That's fine. Whatever you're working on.
I'll have to look at my website real quick.
Okay.
So 1 second.
Try to give me problems that you don't know how to do as opposed to problems that you do know how to do, right? In other words, you don't need help where you don't need help. Where you need help is where you don't know how to do it on your own.
Yeah.
Okay.
Okay, so 1 second. It's kind of laggy.
You're pulling these problems off your computer?
Yes.
Okay. Yeah, and since it's tied up on GoToMeeting, same computer? Yeah, it's going to be a little laggy. In other words, it'll be a little slow because GoToMeeting, first of all, hogs an awful lot of your computer power. So when I'm running GoToMeeting, it's hard to do much else unless you have a really powerful computer. Now, the reason we're using my phone is because apparently the microphone on that computer doesn't work. If you can get that microphone working, the whole thing goes a little better. The audio is actually quite a bit better under the GoToMeeting audio than it is the audio from my cell phone. And it's probably the same on your end. In other words, you're hearing me and I'm hearing you, but it's not as good a quality as if we were using the speaker on your computer. So if you can figure out how to get that microphone fixed between now and the next time we have a session, it'll go a little better. We'll be able to use the computer audio. But for now, the speaker works just fine on the phone. We don't need to worry about it. It might be a situation where your microphone is just turned off on the computer, and you need to figure out how to turn it on. But let's not worry about that tonight. We can.
I've got the problems up.
Okay. Give me the first one.
The first one is graph the following transformation.
Okay.
Transformation is f parentheses x minus 4 parentheses.
And what is f of x equal to?
1 second.
In other words, I can't do anything with that unless they start you off with an f of x.
Yeah. 1 second. Let me get my notes out.
You know what? Let me make up an f of x. Unless you have specific homework that you have to turn in that you want answers to, and then we'll work on your homework. But if we're doing this just to get you to understand it, I can make up anything I want. Let's say f of x was x squared. What's f of 3? What do I do? What do I do with the whatever's inside the parentheses? I plug it in for x, right?
Yeah.
So that's 3 squared, so that's 9. That's what f of 3 is. Well, what is f of x minus 4? Plug in whatever's in the parentheses in for x. That's how you handle that.
Yeah.
Okay. Now, that's not really a satisfactory answer. I have to multiply those two together. I have to multiply x minus 4 times x minus 4, and that gives you x squared minus 8x plus 16. So that's what f of x minus 4 would be in this problem, as long as f of x is that. And it doesn't really matter how complicated f of x is. The solution is always, always plug whatever is in the parentheses in for x. Okay? So I need an f of x on your f of x minus 4. I need to know what f of x they gave you was.
It just gives me f of x minus 4 and it says to graph it.
Well, that's impossible. However, I will tell you what that is f of x translated 4 units to the right. Okay? In other words, let's say f of x was x squared. Well, here's what x squared looks like. Okay? Now, that's x minus 4, which means I'm going to take this f of x and move it 4 units to the right. So my new f of x is going to look like this.
Oh, okay.
Okay? In other words, what this means is a horizontal shift. Now, let's go over these. It's important to know what each of these means. In fact, let me start from the beginning. We have some function f of x that's not defined. We don't know what f of x is. Okay? There are 6 things you can do with that function. There's 3 vertical things and there's 3 horizontal things. Let me do the verticals first. That is a reflection over the x-axis.
Okay.
That is the function shifted up by 2 units. Notice that that's also a vertical transformation.
Yeah.
This is the function multiplied by 3. That's called a vertical stretch. So let's label them. That is a vertical reflection or reflection over x. I like to refer to it as a vertical reflection because you'll see a pattern between all of the vertical transformations and all of the horizontal ones. This is a vertical shift. Does not change the shape of the graph, only moves it up or down. This is a vertical stretch. That does change the shape of the graph. Okay, and now you have 3 horizontal ones. That is a horizontal reflection, meaning over y. In other words, if you take a function and you reflect it over the y-axis, it's a horizontal reflection. Okay. That is a horizontal shift. Does not change the shape of the graph, merely moves it left or right. And finally, the third one is that, and that is a horizontal stretch. And stretches always go with shrinks also. In other words, depending on whether this 4 is a number greater than 1 or less than 1, if it's greater than 1, it's a horizontal shrink. If it's less than 1, it's a horizontal stretch. And the same thing back here. That's a vertical stretch or shrink. It's a shrink if this number is less than 1. It's a stretch if it's greater than 1. And notice that that's different. Vertically, if this number is greater than 1, we have a stretch. Horizontally, if this number is greater than 1, we have a shrink. So they work opposite to one another. Okay? So if I had a function and I wanted f of 4x, I know it's going to shrink by a factor of 4. And what does that mean? Well, let's assume, you're familiar with quadratics, right?
A little bit.
Okay, a quadratic is a parabola. Looks like that. And it's easier to show these on quadratics than it is on linear functions. Because linear functions, a lot of times a vertical shift is the same thing as a horizontal shift. So they're not really good for showing differences. But let's talk about the first one here. In other words, if f of x is x squared, what is minus f of x? And I'll draw it in red. What does minus f of x do?
I can't really see
It's
what
okay. Okay. Well, minus f of x is a vertical reflection, which means I'm going to take my parent function and reflect it over the x-axis, which gives me that. You with me? Can you see everything?
Yeah.
Okay. That's if I had minus f of x.
Yeah.
What if I had f of x plus 2? Well, then I take my original function in black and I just move it up by 2 units.
Okay.
Same shape exactly, only it's been vertically shifted by 2 units. Now let's take the third one, 3 times f of x. Well, that's a vertical stretch, and a stretch does change the shape of this thing. It narrows it. It makes it look like this. It makes that parabola skinnier.
Yeah.
By a factor of 3.
Okay.
Or whatever this number is. If that's 11, it's by a factor of 11. If this is 1.5, then it's by a factor of 3/2. Okay? Okay, so that's how the vertical transformations work. Let me erase what I have here, and I'll show you how horizontal transformations work. So I still have my, let me redraw this just a little bit, make it a little bigger. Here's my parent function. It's the parabola y equal x squared. Now let's go down, and in red, what would f of minus x mean?
F of minus x.
Yeah, read it from the page. What does it mean?
Would it move the
It's a horizontal reflection. All 3 of these below this line are horizontal.
Yeah.
And it's a reflection. In other words, whenever you see a negative sign, it's either a reflection over the x-axis or it's a reflection over the y-axis. In this case, it's a reflection over the y-axis. Well, notice what this thing looks like if I reflect it over the y-axis. Looks exactly the same, right? Yeah, there's no difference. Okay, let's go down, and in blue, let's look at what f of x minus 3 would be. Well, what's it say?
Horizontal shift.
Okay, and it's 3 units to the right. If that's a negative sign, you're going to the right. If it's a positive sign, you're going to the left. So if I take this curve and shift it 3 units to the right, looks like that. Same shape. Haven't changed the shape of the curve, as all I've done is move it to the right. Now in green, we'll do the bottom one. What would f of 4x look like? Is that a shrink or a stretch? Yeah, horizontal shrink. Okay, from my original curve. So let's erase the blue, and in green, I'm going to draw what a horizontal shrink would look like by a factor of 4. It looks a lot like a vertical stretch, right?
Yeah.
They are. They look exactly the same. Except, in other words, you can think of this as if, I pushed on both of those sides, I'm shrinking it horizontally by a factor of 4. Okay? So those are all of your transformations that you can do. There's only 6 of them. Okay? And the key to learning them is right here. Is to know what each of those mean. In other words, you not only have to know the left, but you have to know this part here also. When you see f of minus x, you know that it's a horizontal reflection, meaning you reflect it over the y-axis.
Yep.
When you see f of x minus 3, you immediately know that it's a horizontal shift. So if I take my function here, f of x minus 3, well, I know that that's x minus 3 squared, but I don't really have to multiply that out to figure out how to graph it. As long as I know the parent function looks like this, well then this function I know is shifted 3 units to the right, doesn't change shape, so it must be right there. And that's how you graph them. You don't multiply them out and then figure out how to graph it. You understand what your parent function is. There's only like 10 elementary functions. Okay? There's y equal mx plus b. There's y equals x squared. There's y equal x cubed. There's y equals square root of x. There's y equals sine x. There's y equals, let me think, log of x. All of these are elementary functions. And when I say y, I could just as easily write f of x. F of x and y mean the same thing. F of x is a little more powerful. Notice that I have no way of writing what f of 2x would be. Whereas if I write what I have circled there as an f of x equals x squared, well now I know what f of 2x is. I'm going to plug in 2x for x, and so I'll have 2x squared which is actually 4x squared. Okay? But it's all I have to do is look at that and know that I have a horizontal shrink by a factor of 2 of my parent function. So if I know what my parent function looks like, the elementary function, then it's pretty easy to graph this without actually doing the algebra. In other words, just shrink it by a factor of 2 and you got the graph. Now, some of these elementary functions you probably haven't learned yet. You probably haven't learned that one. Probably haven't learned that one. But you probably have learned the others that I listed there. You certainly have learned y equal mx plus b. And you almost certainly have learned y equal x squared. Probably haven't learned that elementary function, but you probably have learned that one. Square root of x looks like that. In other words, x has to be positive only. You can't take the square root of a negative number. And y is always going to be positive because the square root of a positive number is always a positive number. So the graph of this equation looks like this. It doesn't go to the left of the y-axis and it doesn't go below the x-axis because x can never be negative and y can never be negative. So that graph looks exactly like that. So let's just use this as an example, okay? So I'm going to say f of x equals square root of x. Now tell me what this means. In other words, you have to memorize those things that I laid out, those 6 transformations. At some point, you're going to have to memorize them. You might as well do it now. It'll make this subject a lot easier for you, for everybody. A lot of people try to get through this subject of transformations without memorizing those. Very difficult, very, very difficult. You really kind of have to know that minus f of x means a vertical, because the negative sign is outside the function, reflection. Okay, so if I were to do a vertical reflection of my graph, looks like that. Whereas if I said to you, what is f of minus x, kind of reflection is that?
That is a horizontal.
Just think of it as a horizontal reflection, and then know that that means you're reflecting over the y-axis. Okay. So if in green I'm going to reflect the black curve across the y-axis, looks like that. So this would be f of minus x. In red, I would have minus f of x. And in black, that's just f of x. So whenever you see a negative sign, it's either going to be a vertical reflection or a horizontal reflection. And the way to keep these straight is any transformation that is outside of the f of x is vertical. If it's inside the function, it's horizontal. And I don't know how to get to the previous page here, so let me write them again. In other words, outside the function, vertical reflection. Outside the function, vertical shift
Yeah.
multiplied, which is outside the function,
Vertical stretch.
vertical stretch. Now, let's talk about inside the function. These are all horizontal. If I'm inside the function, that's a horizontal reflection. If I am inside the function, that's a horizontal shift.
Yeah.
And if I'm inside the function,
Horizontal stretch.
horizontal, in this case, shrink, because the number is greater than 1. If the number, not just less than 1, if it was between 0 and 1. In other words, if I had f of x over 2, that's the same as f of 1/2 x. That is a horizontal stretch by a factor of 2. Because this number is between 0 and 1. And you can't just say less than 1 because negative numbers are less than 1. And the moment you put a negative number in there, it means a whole different thing. It means a horizontal reflection. Okay? So when I'm differentiating between stretches and shrinks, I only care if the number is greater than 1 or between 0 and 1. Okay? So here's what you want to memorize, these. And that can apply to any function. It does not matter what f of x is. So the game, we only have a minute or two here, but the game they're going to make you play is this. If g of x is equal to x minus 2 squared plus 3 all multiplied by 4, you got a bunch of transformations going on there. What do you got? First of all, what's the parent function? What is f of x?
That is
x squared. This is the parent function right here.
Yeah.
Okay? You got 3 things happening to that parent function. You got this multiplier, you have this thing being subtracted, and you have this thing being added. So what are those 3 things? What's the 4 do? It's outside the function, so it's vertical.
Yeah, it's a vertical stretch, I believe.
Yeah, vertical stretch because it's greater than 1. And what's the plus 3 do?
Would that also be a vertical stretch?
Vertical shift. The difference between shifts and stretches are shifts do not change the shape of the curve. They merely move it up or down. Stretches do change the shape. They make the curve skinnier usually. And finally, there's one last thing that's being done. There's that. What's the consequences of that?
Is that a horizontal?
We know it's horizontal because it's inside the function, right?
Yeah.
Horizontal shift.
Yeah, that's what I was going for.
To the right by 2 units.
Okay. And then that's being void.
And that's it. There's only 3 things being done to the parent function. You have a vertical stretch, horizontal shift, and a vertical shift. There's no reflections. If I put a negative sign in front of that 4, now you got 4 things being done. You got a vertical reflection, you got a vertical stretch, horizontal shift, and a vertical shift. So you can actually have up to 6 things being done. If I put a negative sign in front of that, now I got a horizontal and a vertical reflection. Kind of getting it? All right. Nick, our half hour is up. I'll let you go, and I will talk to you and your sister hopefully again.
Okay.
Yeah. Have a good night. Talk to you next time.
Good night.
Bye-bye.